Hello everyone, this is Mr. Sim Engineering bringing you part 2 of the AWR 16.0 version of my, shall we say, seminal tutorial series on how to use AWR's Circuit Simulator. I want to mention before we actually get into the nitty-gritty stuff that we're doing here that this is a series that originally was made to help the students of RF circuits at Florida International University to do their final project, and that is still the main inspiration of the series. However, since 2019, when I first made that series, and now I've learned a lot of things in AWR, and so therefore we're just going to be going through a lot of the same material in a more extended format, going into a lot more detail, looking at different techniques of simulation, design, improvement, optimization, tuning, yield analysis, and a whole bunch of other stuff that we can do. This is not a tutorial on active circuits. We're not doing active. RF circuits at FIU only covers passive circuits. In the future, we might get into a little bit of pin diode simulation and stuff like that, but for now, we're only doing passive circuits. And specifically, the first passive circuit that we're going to be looking at today is the Wilkinson power divider. And we're going to be using POSAR 4th edition as kind of our reference point. So specifically, we're looking at page 328, section 7.3 of POSAR's Microwave Engineering 4th edition. And we're going to be looking at these diagrams here. So a Wilkinson power divider is a 3-port device which effectively, divides power. And it can also be used as a power combiner. So as we can see here, and I can even use the little, let's see here, we have comment and pencil, right? So if we're looking at it as a power divider, we're looking at the input port here, call that port 1, and then obviously we're going to have this junction here where the power splits off in two possible directions, right? Going into quarter lambda or 90-degree electrical length lines of impedance root 2 of the characteristic, then going into these kind of exit lines. And we also have this shunt resistor here that is 2 times the characteristic, which is used to limit the coupling between the 2 exit ports. Okay, so that's kind of where we're at. And specifically, the type of Wilkinson power divider that we're going to be designing today is an equal power Wilkinson power divider. And if you see my Steam popping off, please don't mind me. Let's actually go ahead and exit my Steam. If you want to add me on Steam, leave a comment below the video and I'll see if I can add you on Steam. So anyways, that's kind of the point of what we're looking at here. We're going to be doing an equal power Wilkinson power divider. There is a way to do an unequal one. If we skip past the even odd mode analysis, there is a section here called Unequal Power Division and Way Wilkinson Power Dividers on page 332, which goes into some of the design principles and how to do an unequal power divider. But today, we're specifically looking at the first design here, which is just your equal Wilkinson power divider. This is an equal one, right? It says subsection A. Subsection A, it's an equal split Wilkinson power divider in microstrip line form. So now, let's go into AWR and get to work. So the first thing that we're going to do is, looking at a fresh project here, as we did last time, File, New with Library, AWR Example Libraries, AWR RF Board to Layer. And today, specifically, we're going to go into project options. We're going to talk about the frequency range. Let's simulate from 2 gigahertz to 2.8 gigahertz, which is going to make our center 2.4 gigahertz, which is the Wi-Fi band, and we're going to say a step of 0.02 gigahertz, which gives us 41 data points with data entry set to units. So we're going to go to global units here, edit the units, make sure that frequency is set to gigahertz, which it is. We're going to go ahead and hit OK, OK. Now that's set up that. We're going to double click on here. We're going to select our substrate here. And it's currently selected RO for 4350. We're going to right click, disable that. And then we're going to right click on 4003 and enable that. And then we're going to go ahead here and we're going to work with 31 mil because I have some 32 in the lab. And so I'm just trying to kind of match it with what I'm normally kind of used to using. Let's say 0.79, and we're going to leave the thickness of the copper layers to be 1 ounce copper, which is 0.03556. And we're just going to leave that as it is, okay? And then the rest of everything is already set up for us, which is nice. And so the first thing that we're going to do is we're actually going to go to Circuit Schematics. We're going to create a new circuit schematic, and we're going to call this one Ideal, because we're going to be doing an ideal representation of the Wilkinson power divider. And so we're going to introduce a new element. I'm using the element button that we talked about in part 1. And specifically, I'm looking for T-line P or T-lin P, which is physical spec. And we're going to drop that in here like that, which is perfect. Oh no, again, I tried recording this before and I actually made the same mistake 2 times in a row, and we're just looking for T-lin regular. So just this one here is the grounded shield closed form. We're just going to go ahead and drop that in like that. And just to make our life a little bit easier, we're going to set the center frequency F0 to 2.4 gigahertz. And then from there, we're just going to work off of the rest of the stuff here. So cancel that. Copy, paste, I'm going to paste it over there, and then copy, paste, I'm going to paste that over here, because these are basically the exit lines, and they're all kind of like the same length. And matter of fact, I actually want all 3. So what I did is I just selected them all with shift click. Again, watch part 1 if you haven't already watched it. And then we're going to go in here and we're going to set the electrical length to 180, right? Because 180 basically makes the phase effect non-existent, or at least what it looks like non-existent from the S parameter perspective. And then we're going to go ahead here, we're going to copy and paste this. We're going to put a vertical here. This one is, again, length of 90 degrees or quarter lambda. And the impedance is root 2 of 50. Root 2 of 50, 70.71. And if you do enough RF work, you're just going to memorize that value, and you're just going to keep it in the back of your mind because you're going to use it a lot. So then I basically just copied and pasted the other one here and just dropped it in like that. And I'm going to pull this one here, and then I'm just going to pull this one up here. I'm going to drop that junction connection there. I'm going to connect this here, and I'm going to connect this there. And then I'm going to go back into the Elements browser, RES for closed form resistor. We're going to hit OK on that. I'm going to drop that here. And again, it's 2 times the characteristic. That's 100. And then I'm going to go ahead and just drop that in there and drop this in here. And now we basically have the base structure kind of dropped in here. And then we're going to grab some ports off the top here, 50 ohm ports. Go ahead, set it up, copy, paste. You can right click to rotate. Again, watch part 1 if you haven't done that already. And then beam bam. This is what we're looking at. This is the design that we're going to be doing for an ideal representation of the Wilkinson power divider. Again, now we're going to do some graphs. Right click on graphs, new graph. We want a rectangular this time, unlike the Smith chart we did last time. And we're going to call this one reflection coefficient. And then we're going to right click on it. We're going to add measurements. And specifically, I'm going to leave it as all sources, because then we're going to do the microstrip representation, and that'll just automatically show everything on the same graph, which is actually nice. And we're going to make sure this is in magnitude and in dB. And we're going to go ahead and click add, and then we're going to select 2, 2, add 3, 3, add, and then just close, right? So then we're going to go ahead, go up here to the simulate button. We're going to hit simulate, and that's going to simulate everything for us. And then here we're looking at the 3 ports matching, which in this case, we're gonna, I'm not sure if I explained this in the other video, but what you can do is you can double click on these corner values, and that'll allow you to set the upper limit and the lower limit. So we're gonna double click on that and 0. That's my one lower limit that I'm interested in. And the other one, we're just gonna leave it as default here. That's fine. And then basically what we're looking for here is, are we less than negative 10 dB? For that S11, or even better, are we less than negative 20 dB, which is an even better match by like 1 order of magnitude. So effectively what we're going to do here is, if we really want to see that, we can right click here and then do add horizontal line marker, and we're just going to drop that anywhere. And then what you can do is you can mouse over it, right click it, and do move line marker, and then type in the value that you want, hit move, and then close the window. And so here we can see that negative 10. I'm going to go ahead and add another one here just to show it again. Right click on the thing, move line marker, negative 20, hit move, and then close the window. So here we have for port 1, 2, and 3 a match for S11 of basically more or less, shall we say, the value, the S11 in dB magnitude is less than -20, which is a very, very good match. And matter of fact, at 2.4, the match is very, very good here. Again, you can kind of mouse over a trace, and then when you click and hold, you can see the value. So at 2.4, we're actually looking at -100 dB. That's a very good match. And then over here for the other two, which is port 2 and 3, we have -106.4 dB. So that's absolutely fantastic. So now we showed that, which is very good. Next, we're going to do a new graph, and then we're going to look at, this is going to be the insertion loss, or transmission coefficient, however you want to refer to it. We're going to right click on that. We're going to add measurements, and specifically the ones we're interested in here is to port 2 from port 1. Make sure it's mag dB. We're going to hit go right ahead on that one. And then to port index, we're going to do 2, 3 from 1. We're going to hit add, and then boom, we have those two. And then we're going to hit that simulate key again. We're going to change the upper limit to 0, and then we're going to change the lower limit to about -10. And then we can see here that we have at 2.4, we basically have the -3.01 dB, which is basically what we're looking for. Again, -3 dB in linear is half. So again, it's an equal power divider. It's a two-way power divider, shall we say, right? So it basically goes two ways. So if you take something divided by 2, then that's half on each side because it's equal split. So we have -3 dB. Even if we go all the way to the left edge of the band, we've got -3.047. That's very nice. And all the way at the top end of the band, 2.8, we're looking at -3.047. So again, this is bang smacking awesome. Now, the thing is, we need to understand that, again, we're doing an ideal simulation. This is not a realistic simulation of what you're actually going to get in the case where, you know, you're actually going to fabricate this and use this. Sorry, I was taking a sip of coffee there. So now we're actually going to do a microstrip simulation, okay? So what we're going to do is we're going to create a new circuit, new schematic, and we're going to call this one Microstrip, and we're going to go ahead and create that. For this, we're going to need a couple more components. We're going to need mlin, boom. We're going to need MT. I'm going to use the regular one here, not the intelligent one, which will automatically track what the values are. I want mbend, and specifically it is 90. No, it's unmitered. Come on, which one is it? It's I'm drawing a blank right now. It's mbend 90x. Mitered, yeah, it's this one. We're just gonna right click, just drop that in the right spot here, and then what we're gonna do is, of course, we also need our resistor. We're gonna use the resistor here. Resistor, drop that in there. Look at that, it's beautiful. It's a beautiful resistor. I love it so much. It's perfect. So there's two ways. There's two ways to synthesize your dimensions for your microstrip, right? Because we have to convert an impedance to a width on the microstrip, and we need to convert the electrical length to a length on the microstrip. So there's two ways to do that. If you watch the old 2019 tutorial, the only real way to do that was using TX line, which is still available to you. If you go to tools, you can open up TX line. It's right here. It hasn't gone anywhere. You can use that. But now in 16.0, we can do a cool thing. You can just right click on a value and just go synthesize, and you're going to be able to do it through here. So we're going to do that synthesis here for the feed line, so you can see how that works, just so that if you want to use it, you know that the option's open to you and that you know that this is an accessible way to do it. So the way this works is you can expand this window and just make it a little bit bigger if you want. You're just going to check off for width and length the synthesize box, right? And then the target, you're going to check Z0 real, Z0 imaginary, and electrical length. You're going to target those three values. So these two here, the real and imaginary of Z0, correspond to the width, and then the electrical length corresponds to the length. So what this is doing is it's reading the substrate values, which if you look up here, you can see this layer 01 underscore CU for copper underscore 01. It's reading that microstrip substrate definition that's already in the global definitions that we've seen before. It's just reading that, and it's doing all those calculations in the background, and you don't have to punch in the values yourself, saving you some trouble. So effectively, it's just a nice little thing to have. So we're going to go here into Z real or Z not real. We're going to hit 50, and then we're going to click on imaginary. We're going to hit 0, enter, and then electrical length. And in this case, it's the feed line, so we want 180 degrees. We're just going to set that to 180 degrees and hit OK. And wow, I made a mistake. Okay, so what you're supposed to do is you're supposed to synthesize with length, Z not real, Z not imaginary, Z not electrical, and you're going to go 50, enter, and then you go imaginary 0, and then you go 180 for the electrical length, and then you're supposed to hit the left arrow that says synthesize. If you go the other way, it'll analyze the width and length for the given values in question, and then what it'll do at that point is that it will basically give you the corresponding real and imaginary values for the impedance, and it'll also give you the electrical length in degrees. Also, double check and make sure that your synthesize frequency is set to 2.4 gigahertz specifically, so that it will actually put that as your center frequency. We're going to go ahead and again hit synthesize. You'll see these values update here. That's fine. They've updated. Now we can hit OK, and you'll see that these values are reflected here. That's the new way to do it. The old way to do it is, let's go back to the global framework here just so we have these values available because we're going to need them. We're going to go to Tools, TX Line. We're going to bring it over here. I'm going to move through this one quickly because you can watch this in the old tutorial series. Literally just copy over your values. 3.55. What's my loss tangent? 0.0027. Set your conductor to copper. What's the frequency? 2.4. What is the impedance we want? 50. What's the electrical length we want? 80. 180. What's the height of the material? It is 31 mil in this case. What's the thickness of the conductor? It's 35.56 micron. And then you hit that right arrow, and it'll update your values. So again, if we go back to here, let's close some of this stuff. If we go back to Microstrip, we compare the values. Where's TX lines? Right here. We can see here that the values are pretty much about the same, right? So for the width, it's 1.726. We have 1.720. And for the length, 37.52 basically, and here we have basically 37.52. So the difference is minuscule. Again, all the same information you can get from the synthesize window, you can actually get from TX line as well. So that's great. So now let's kind of do some work here. Give me 1 second here. Let me take a sip. Got to have your coffee. It's very important. Okay. So let's get to work. So last time when I did 2019 video, I used variables, store the values in variables, and then go from there. Today I'm going to do it differently because, again, you can go watch the old video, learn how to do it with variables. In today's video, I want to teach you how to use tags to basically pull information from other components on the same circuit so that you don't have to create variables. Right. So I'm just going to show you guys how to do that. In order to facilitate that process, what I'm going to do is I'm going to give these components actual IDs to identify them, which you can do. Again, the ID here, for example, if we're looking at MLIN here is TL1, you can change that. You can double click on that, and we're going to call this port 1 feed. That's it. That's all we're going to do. We're going to call it port 1 feed. And then now we can refer to this Microstrip line with the ID of port 1 feed, and we can pull its width and we can pull its length, as you're going to see that we're going to do. I'm just going to unite those two things. Now I'm going to grab that, copy, paste. I'm going to drop it in there, and then I'm going to change the ID. We're going to call this one port 2 leg 1 because it's the first part of the leg before this bend here, and then you can copy it and paste it. And the number at the end will actually increment by itself. So it's port 2 leg, the second part, right? Now, let's actually delete that one. Let's go here to this one, right click, synthesize. So again, the whole leg is quarter lambda, which is 90 degrees. So that means half of the leg, right? Because we have the vertical component and the horizontal component after the bend. It's half. So we're looking for, first of all, width length, synthesize the real and imaginary and the electrical length. And again, it's going to be 70.71. Then the electrical length, it's not going to be 90, it's going to be 45 because it's half and half. And then we're going to go ahead and synthesize those values. See these things update over here. We're going to hit OK. Now those values have been updated. Now we can literally just copy and paste these and paste it over here. We see the ID has already updated. Now here's the thing. Let's say I want to optimize these values later, which we will do because we want to improve the performance of the Wilkinson power divider. What we're going to do is I need these two things here to always have the same width. So and I also need the bend to have the right width. So I'm going to go ahead and let's start with the bend. The width of the bend is going to be the W value, the width value at, using the at symbol, the mlin with the ID of P2 leg 1. Now that's going to copy this width into that space. This is what I meant by tags. And then I'm literally just going to double click on that and Control C for copy and then deselect it and then double click on there, Control V and deselect it. And now I've copied that value. And we're going to do the same thing here with length. Length at mlin of ID P2 leg 1. So now we'll see that these two things have the same width. And we can check that by going up here to where you have the element button and the port button and then selecting layout. Then here in this view, I'm going to control zoom out. So basically control scroll down, Control A, and then go up here and we're going to do snap together. And that's going to snap everything together. Okay. And then I'm going to go to the layout view here in the bottom left, and I'm going to scroll through the layers here on the left-hand side. I'll probably be zooming in at this point. And what you can do is deselect the visibility for copper 1 negative and copper 1 positive. And then we're also going to deselect it for copper 2 negative and copper 2 positive. Don't worry about that. It has to do with some kind of like safety margin thing that is built into the software. So don't fret about that too much. Then what we're going to do here at empty is, again, we're going to do the same thing we did before. Double click on this, copy the width tag that we used before. And we're just going to go in here and we're going to literally say that port 1 is that, port 3 is the same, right? And then port W2 is W at mlin of port 1 feed. So now we've copied the width of the feeding line. Oh, I did the wrong one. So this one is supposed to be port 1 feed, and then port 2 is supposed to be P2 leg 1. Just update that. We're going to hit Control Save. Oh, we haven't saved the project deck. Look at that. Let me just save it over the project I had already actually started last time and I didn't finish the video on. So we've already done that. So now if we go back into the layout view and hit Control A and we snap everything together, we can see that everything lines up, right? We basically inherited the values of the different components. Awesome. So we're already ahead quite a bit. We're going to take this junction here, copy it, paste it, rotate it, and aim it down, because the thing is we have to put the resistor, right? But there has to be a line there to connect the resistor to. Remember, this is probably going to be a chip resistor or maybe even a through-hole resistor. And so you need to have a way to get the signal, the RF microwave signal from, you know, the junction up here, right? You have to get it down to the resistor. So we're actually going to have a line, which in the ideal representation, we didn't need to do that because it's ideal. It has no physical representation. But in the microstrip, we do have a physical representation, because we go here, we snap all these together. What you're going to see is that we're going to have to, you know, the resistor is going to go somewhere around here. So we need a way to get down to that spot so that we can actually put the resistor in, solder the resistor in. So we are going to need a junction here. And the width there for port 1 is going to be P2 leg 1. That's correct. Port 2, P2 leg 1. That's not actually going to be it. We're going to call this one P2 feed. And then the W3 is going to be P2 res, right? So P2 resistor. Okay. And what we're going to do here is I'm literally just going to copy this feed line and I'm going to go ahead and paste it over here. And I'm going to let it have its own unique width and length, because later when we optimize, we might actually need that. So we've dropped that in there. And then I'm going to go ahead and copy this. And actually, let's delete that here really quick. And then what I'm going to do is I'm going to grab this P2 leg 1. I'm going to copy that one and use that one as my feeding leg. And again, we're going to call that P2 res for basically the leg that feeds the resistor. I want the length of that leg for now to be the same as P2 leg 1. Right? So it's going to have, and I forgot the mlin tag, mlin dot. And then the width, we're going to leave it be the same for now. We're going to let it be the same. And then basically I want to reflect this entire thing on the bottom portion there. So what I'm gonna do is let's try to do that. I'm gonna copy, paste, and then you can literally just select everything, and then do flip, and go like that. And then we're just gonna, wow, look at that. It's beautiful. That's beautiful. And then it should work if I do snap to, nope. That broke it really, really bad. So let's actually just do it manually. It doesn't even take that long to do. We're just gonna copy this here. We're gonna go bum bum, rotate it around. This is gonna be P3 leg 1. And in this case, I want the legs to have the same width. So again, I'm just gonna say W at mlin P2 leg 1. Same length, L at mlin dot P2 leg 1. We're gonna grab this corner here, rotate it into position, right? And then we're gonna grab this here, copy and paste it in here. And then I'm gonna grab this here and I'm gonna rotate it around and just move it over here. And effectively, the only one that we have to change here is port 3. It's gonna be P3 res. We're gonna copy these here and we're just gonna drop that in there. Doesn't really matter that much. Again, this is P3 res. A lot of this is just, you know, cleaning up and stuff like that. Again, this is a symmetrical design, so I'm gonna go ahead and copy this over here and then we're just gonna leave that there. And this will be P3 feed. And again, what I'll do is I want these two to reflect each other. Why? Because it's a symmetrical design for an equal split power divider. mlin P2 feed, L at mlin dot P2 feed. So that way, these two here have the same width and the same length. And then what we do here is let's go into the layout, Control A, anchor everything together. Something went wrong here. What happened? Okay, there we go. Now we actually had everything snap open properly. So we have to fix some things here. So the port 2 width is actually W at mlin P2 leg 1. And then port 1 is W at mlin dot P3 feed. And then this is going to be W3 is P3 res. So then we go in here, Control All, and update it. And okay, cool. So now you see the symmetry, all the symmetry's there, perfecto. And we're gonna make sure that our resistor value is 100. And then all we're missing now is the ports. We're gonna grab the port here, grab that label, copy, paste, paste, drop it. So now we have all the values here. Now the cool thing is, again, we now have the microstrip representation. This is the physical layout of it. Okay, so again, you have the feed line, go up the leg, right? This is your root 2 of 50 leg, the line that feeds the resistor, where the resistor is going to go here. And then you have your exit line or your feed line, because again, it can be a power combiner. If you feed 2 signals into the symmetrical legs, they'll combine at the junction and you'll feed out as a power combiner. Or if you feed the input here, the single line, it'll split off the junction and you'll have a Wilkinson power divider configuration. So let's go to the insertion loss first, because it's the first one on the stack. And we're gonna go ahead and just reduce this a little bit here. We're just gonna go ahead, simulate. So we see this brown, this red. This is the microstrip version, which has 3.5 dB of insertion loss. So it's supposed to be about 3. We have about 3.5. Again, remember, this is a real microstrip. There's attenuation in the microstrip, right? Microstrip lines, real transmission lines, are not lossless. They're lossy. So you're going to have a little bit of additional loss. So here we're looking at about 0.5 dB of loss specifically. We're going to open up the reflection coefficient ones. And again, the simulation already ran. And specifically here, we're looking at the fact that the ideals are very low, right? The ideals are very low. I think right here, you can actually, nope, it'll just disable both. So what we're going to do here is I'm just going to take this bottom limit and I'm going to set it to like -20. Okay, that's not enough to really kind of capture what we're looking at. So let's say about -30. Okay. So we can see here that the green and the black are ports 2 and 3. These are sub 20, sub negative 20 around that center frequency. But even then, across the entire band, we have sub negative 10 matching, which is very nice. And then this port 1 here is definitely sub negative 10. So it's very good matching. The one we didn't look at before, let's do a new graph here, is going to be called the coupling. And we're going to just literally look at 2 port 3 from port 2, add that for all sources, and then just flip those as well to see if we have reciprocity. And then we're just gonna run the simulation here. And again, for the ideal, very, very, very good coupling, right? Like there's negative 10, there's negative 100 dBs worth of connection, power transfer there. While with the actual implementation, even then it's like, again, negative 10 dB. It's quite a bit, right? So what that represents is basically like 1/100th in linear. So, sorry, 1/10. That's 1/10, and then it's almost 3 dB, so it's actually 1/20th of connection between the ports. And we can improve that by doing some tuning, which, matter of fact, let's do a little bit of tuning. Let's do a little bit of tuning. So what we're going to want to tune here is, I actually want to see what changing the width of these lines, and actually these should be matching now that I think about it, w at mlin.p2res. I want to match those. So right click here, properties, tune the width, or hit OK. And then only control save to make sure that everything is saved. I'm going to open up this view here, and then I'm going to pull up the tuning window, which we already talked about last time. And let's see what happens here. So as you make the line thicker, you reduce the impedance of the line looking in, right? So that's basically the resistance kind of goes down, right? So as we increase the resistance, or as we decrease the resistance there, we can see the line dropping more and more and more. But now I'm curious, right? Let's set the upper limit to like 5. Some absurd width, right? And then we'll say 3. Okay, so it just keeps going down. 5, it keeps going down. So now we know, we go back to let's actually close this one and close this one. So you see, obviously, right, if we update the widths, right, you see it's stupidly absurd. That's like 5 millimeters wide, right? Proportionally speaking, it's very absurd, right? But effectively what you're doing is you're maintaining the resistance of this here. So the resistor itself is the same value, but you're making these, the feeding lines that feed the resistor, you're making them have a lower impedance. Okay, so effectively you're making it so that you have a more readily, so that resistor is more readily accessible from a wave perspective because you're reducing the impedance of the line. So, when the wave is traveling around, it's like, hey, this track has a considerably lower resistance, so we're going to go down this way, and then it's going to hit the resistor, right? So now let's do another thing here, right? What we're going to do is let's go back to the microstrip view, and let's set the value to 0.92 again. And what I want to do this time is I want to tune the resistor itself. We're going to hit OK on that, and we're going to go back to coupling. We're going to go ahead and run the simulation again. What happens if let's close that. If I increase the resistor, the high end, so if you look at the right side, that dips first. So I'm improving the coupling at the higher frequencies, but the lower frequencies are also moving, but not as much. So that's the other option that we have, is to increase that resistor. But let's take a look at the other values, insertion loss and reflection coefficient. So the matching is actually improved. So if we look at the reflection coefficient, we've actually gotten, if we go back to 100 ohms for that resistor, the port 2 and port 3 was much better with 100 ohms. So if you need less coupling between the ports and you can afford the match sacrifice here, it's still -10. So that's not bad, right? But if you need that isolation, or sorry, you need the better match at ports 2 and 3 for whatever reason, you can always up the resistance of that resistor, of the chip resistor that's going to go on the Wilkinson power divider. That's going to improve your match. Another thing, let's look at the insertion loss. What happens when I mess with it? So the insertion loss is exactly the same. Nothing's happening there. So your insertion loss is going to be identical no matter what you do with the resistor. So again, kind of like, look at what we're doing here, right? We're playing around, changing values. Hey, what happens if I do this? What happens if I do that? Feel free to do that. Experiment, explore, see what changing the different values does for your simulation. And it's going to allow you to really get a very intuitive understanding of different designs, because now you're not just playing with numbers on a piece of paper, you're actually looking at these simulations, you're looking at how the dimensions change, you're looking at how tuning a certain value changes a certain part of the design, whether that's the coupling or the insertion loss or the reflection coefficient. So again, having a tool like AWR at your disposal allows you to kind of get away from textbooks a little bit and get away from that piece of paper and a pencil and actually see things happening and watch curves change and values change as you alter the underlying component parameters. So I'm going to end the video here, because next time we're actually going to get into doing some method of extraction, a little bit of EM simulation. We're going to get into a little bit of footprint design, possibly in the next 2 parts, right? So part 3 and 4 are going to talk about that. And then once we're done basically completely with the Wilkinson power divider, we're going to do a one video that's going to do the hybrid coupler, the 4-port coupler. We're going to do that in one sitting. So that's going to be maybe an hour video, but we're going to start from 0. We're going to do the ideal representation, and then we're going to do the microstrip representation, and then we're going to do the EM simulations, and we're going to do the optimizations and the yield analyses and all that stuff. We're going to do that in one video. So for the next 2 videos, we're going to be doing a lot of EM footprint design, how to, kind of do your 3D structures and stuff like that. And, get further with what we have here, which is the equal split Wilkinson power divider. If you have any questions, leave them in the comments below, or reach out to me via email. If you're one of the students, please email me. You have my emails, or you can reach out to me on Canvas. If you're on YouTube, again, comment, and I'll get back to you as soon as I can. Thank you very much for watching the video. Mr. Sim Engineering signing out.